You're watching a Channel 98 NBISD TV production.
Welcome to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy. Now, if you're a seasoned veteran of watching the show at home or you've tuned in for the first time, welcome. Thanks for watching. Today, we're going to be finishing up our conversation on polynomials. We've been looking at them the last couple of weeks, and today we're going to learn how to find the last of the types of roots that are out there. And they're going to be a little hard to find because some of them are imaginary, but I'll tell you what all that's about in just a second here. So, if you're going to stay tuned, why don't you download the worksheets that I made for today's show from the district website, get a sharp pencil, and play along with me right there at home in your living room from the safety of your living room. Let's go. Okay, lesson 16 today, polynomials. The last of polynomials. We're going to be finding the complex and the irrational roots. Now, there's a lot of theorems that we're going to talk about at first, whose implications will help us answer these questions. So let's look at the first important theorem of today. It's called the irrational conjugate theorem. Now, irrational doesn't mean doesn't have a level head. Irrational in this case means it's a non-terminating, non-repeating decimal, something that can't be expressed as a ratio of two integers. So that's irrational, non-ratio. So the conjugate means that they're going to happen in pairs. And let me show you what that's about. It says in a polynomial, we'll call it p of x, with rational coefficients, if a plus the square root of b is a root, then so is a minus the square root of b. And green seemed like a good color when I made this, but it's hard to show up. There we go. If a plus the square root of b is a root, then a minus the square root of b is a root. So these irrational numbers, the square root of b, like the square root of 2, the square root of 3, the square root of 5, things that aren't perfect squares, are going to happen in pairs. One of them is positive and one of them is negative. And we call these conjugate pairs, a plus or minus the square root of b, provided that, of course, the square root of b is irrational. Now, what's the implications of that? Well, irrational roots happen in pairs when we have rational coefficients. Let's see what happens. We want to find the exact value of all the roots of this polynomial, which is 3, 2, 1 in descending order, or 0 actually. So this is degree 3. So the fundamental theorem of algebra, remember, tells us that we're going to have 3 solutions. Well, I'm telling you that x equals 1/2 is a root, and that's a rational number, and 2 plus the square root of 6 is a root. We want to find what are the other roots, and then what's the factorization? Well, the irrational conjugate theorem tells us that if 2 plus the square root of 6 is a root, then 2 minus the square root of 6 must also be a root. So that's one root, there's the second root, there's the third root. That's 3 roots for degree 3 polynomial. Fundamental theorem of algebra says that's all of them. Okay? Now, what is its factorization? This is going to go back to the factor theorem. Remember, the factor theorem is an if and only if statement. It says basically if we know what the roots are, then x minus those roots are going to be factors. Or if we know what the factors are, then we know the roots. So since I know the 3 roots, let's go to the factorization. So f of x is going to equal, I'm going to leave a little space here in the front. If 1/2 is a root, then x minus 1/2 is a factor. If 2 plus the square root of 6 is a root, then x minus the quantity 2 plus the square root of 6 is a factor. And if 2 minus the square root of 6 is a root, then x minus the quantity 2 minus the square root of 6 is a factor. Now, notice one thing about this. Having the linear factorization is great. But if you expanded it out right now, you're going to get an x times an x times an x. That's going to give you a 1x cubed. If you look over here at our leading coefficient in our cubic, there is a 2 there. So what we'll need to do then is put that scalar multiple, it's not a root, it's just a number that we're multiplying by, in front of the whole thing. And that'll give us our 2x cubed. So that's the linear factorization. We're staring at the factors, so we're staring at the roots. We're staring at the roots, so x minus those are the factors. Now what we can actually do, and I'll do this in a little bit, is we could then, if we wanted to, we could expand out these conjugate factors. And when you expand out conjugate factors, interesting things happen. You basically get a factorization that'll be a quadratic, but it'll be a little bit prettier. It won't have these radicals involved. Okay? So the complex or the irrational conjugate theorem says if you have an irrational root, like square root of 6, square root of 2, then you have its conjugate, negative square root of 2. Okay, that's the first one. There's another very closely related theorem that's just as important. It's called the complex conjugate theorem. Complex numbers are basically, remember, all the numbers that contain real numbers and imaginary numbers or any combinations of the two. And this is the conjugate theorem. So here's what it says. If we have a polynomial, again, p of x, that has real coefficients, not imaginary coefficients, then if a plus bi, and remember that's the standard form for a complex number, a is the real part, bi is the imaginary part, and I is the imaginary unit. If I know that a plus bi is a root, then a minus bi, its conjugate, is also a root. So the imaginary roots, positive I and negative I, also happen in pairs. So you can't have one without the other. That's very, very important. So irrational roots and imaginary roots, essentially, when the I is present, happen in pairs. Got it? That means two of them, plus or minus I, plus or minus radical. Let's look at an application of both theorems that involves creating an equation. Here we go. Here's the instructions. We want to write a polynomial, call it h of x, of lowest possible degree, so we don't get carried away, whose roots are negative I plus 2, negative square root of 3, and 4. Let's think about the theorems we just talked about. If negative I plus 2 is a root, that's a complex number with an imaginary term. We know it's going to have a partner. Now what you don't want to get hasty and do is just change the middle sign. It's not negative I minus 2. You must be careful to change the sign of the imaginary unit or the irrational unit. So one thing that I would recommend is rewrite it in a plus bi format. So really this root is the same as 2 minus I. Well, the complex conjugate theorem tells us then that 2 plus I must also be a root. They have to happen in pairs. Now the negative square root of 3 is a root. Square root of 3 is irrational. So we also know that x equals positive square root of 3 must also be a root. Now 4 is just a rational number. So he's a singleton root. So what are the number of roots that we have to have? Or how many? 1, 2, 3, and here's my fourth one, and then I have x equals 4. So that's 5. 2 pairs and a singleton. So this has to be a degree 5 polynomial. That's the first key step, figuring out what the degree is. Well, now the factor theorem comes into play. If we know the roots, we know the factors. So let's go ahead and write the equation. So I get h of x equals, it's going to be x minus x minus x minus, all of them. So I get x minus, let me go ahead and do x minus 4, get the easy one out of the way. Now the other ones are going to be the complex. So what I'm going to do is I'm going to do x minus, and I'm going to go ahead and distribute the negative. So I get x minus 2 plus I, and then x minus 2 minus I. So those are my two complex factors, and then I have plus or minus square root of 3. So let's go ahead and do that. It's going to be x minus the square root of 3 and x plus the square root of 3. And that gives us 5 linear factors. Now, you could stop there. That is essentially the linear factorization of it. But most teachers and most textbooks want you to expand it out to a certain extent, if not all the way. It's typical to expand your imaginary factors and your irrational factors just to make it look a little bit prettier. You're going to get rid of the i's and you're going to get rid of the radicals. So let's go ahead and do that. And this gets a little bit time consuming, but it's a good chance to practice our routine expansion. Remember, FOIL doesn't work here. So I'm going to start with this x and distribute it to all three of these. Then I'm going to take the negative 2 and distribute it to all three of these. Then I'm going to take my I and distribute it to all three of these. So here we go. Carefully now, I get x squared minus 2x minus ix. And then I move to the 2, negative 2x plus 4 plus 2i. And finally, I get plus ix minus 2i minus I squared. All of that right there is the expansion of these two. Woo! Okay, pays to do it carefully, pays to do it slowly, pays to do it deliberately. Now, you're going to know in a little bit here if you did it correctly. Let's look at these two here. These are the product of two conjugates, and look what happens. I get an x times x, that's an x squared. By design, the product of two conjugates, the middle term should cancel out. So it's going to be a minus square root of 3x plus square root of 3x. That's a zero pair. They're gone. And all we're left with are these last things. Negative times positive is negative. Square root of 3 times square root of 3 is 3. So we say that this is an irreducible quadratic factor. It's not the prime factorization in terms of the linear factors, but we got rid of the radicals. Now, remember I said you'll know if you did this part correctly. Let's go ahead and simplify. I'm going to rewrite everything, so I'm working down equivalent statement all the way down. So I got an x minus 4. Now, as you go through here, if you expand it correctly, everything that has an I in it should cancel out. Okay? I only have one x squared term. He's in the front. He's good. Now I'm going to go through and look for my x terms. I have a negative 2x and a negative 2x right there. That's a negative 4x. If it's helpful for you, you can kind of gently cross out the terms that you're using or underline the ones that are common and then cross them out. Whatever you think is going to help you be a good record keeper, which is all we're doing at this point. Now notice here I have a negative ix and a plus ix. So this here and this here make a zero pair. They're gone. They're opposite signs. So that's a good sign. 2i minus 2i. Here's another I term with its opposite that go to 0. And then I have a 4 and a negative I squared. Well, the negative I squared doesn't cancel out with anything. But remember this. I squared, by definition, is negative 1. You can't square a number usually and get a negative unless you're talking about imaginary numbers. Okay? So I squared is negative 1. And remember, we shouldn't ever leave any value of I with an exponent larger than 1 in our problem. So if I call I squared a negative 1, this becomes negative 1 times negative 1, or positive 1. I can add that to the 4 to get a 5. All right. And now I'll bring down my x squared minus 3. And from there, we basically have two irreducible quadratic factors and a linear factor. And if you need to go further from here, you would just be hitting it with the sledgehammer. It would be a very routine, long, laborious process. Okay? So I'm going to go ahead and stop there. But again, be careful when you're taking inventory on given roots. Are any of them complex? Do they have an imaginary part? Are any of them irrational? If so, you're actually implicitly given their partners as well, their conjugate pairs. And you have to include them. You're going to get the wrong answer. Okay? We don't want that. Let's take a real quick break, watch these very valuable public service announcements. But don't go away, because we're going to be right back with some more Deja Vu. It's Algebra 2. While you're going to think about this, why was the number 6 afraid of 7?
There comes a point in your life when you realize you're not a kid anymore. Suddenly, you have to make decisions. You have to make choices every day. This is the time when you define yourself, or you let others define you. You quickly learn that there are two ways to go: under the influence or above the influence. I am above the influence.
My cell phone number and John's cell phone number. Hey, pretty. And the number of the restaurant where we're going to be. And oh, I've left you my pager number too, just in case, because you never know. John, you have the gift?
The odds of a babysitter calling 911, 1 in 1,400.
Anything should happen, please don't hesitate.
The odds of a child being diagnosed with autism, 1 in 150. You know the odds of autism. Now learn the signs. Go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corpy, talking today about polynomials, complex roots, and rational roots. Now, why was 6 afraid of 7? I'm sure you're wondering, why would one number be afraid of the other? Well, it's because 7, 8, 9. Okay, so we looked at two important theorems that both dealt with conjugates. And those dealt with basically irrational numbers and imaginaries. Okay? Well, now we want to kind of step back into the relatively nice numbers, the rational numbers, because long before graphing calculators, finding roots to polynomials was kind of the main task of the day. Calculators have kind of trivialized the whole effort, but finding roots was not an easy thing to do. You could actually take any value of x, kind of plug it into an equation like this, and keep your fingers crossed and hope you get a 0. If you got lucky, you found an x-intercept. But there were ways to kind of limit the type of choices that you would even consider of being zeros if you were looking for specific types. And this next theorem is one such theorem that helps us kind of narrow down the search of the possible contenders for relatively nice solutions. And by relatively nice in this case, I mean rational numbers, like 2/3, 1.5, or number 7. Here's what it says. It's called the rational root theorem. And again, rational doesn't mean level-headed thinking primate like this. It means able to be written as a ratio. Okay? Here's what it says. It says if a polynomial has rational roots, if there happen to exist rational roots, then they'll be of the form, and let me zoom in here so you can see it, they're going to be of the form P divided by Q. That's a quotient. Well, what are P and Q? P is a factor of the, here we go, constant, the last number without an x, and Q is a factor of the leading coefficient, the number that's out in front. Okay? So let me go through that again. If it's going to have a rational solution, that means if it happens to already be there, we just don't know what it is, it's going to be of the form P over Q. It's going to be a factor basically of the constant over a factor of the leading coefficient. Okay? Let's go ahead and look at an example. We want to first of all list the possible rational roots, and then once we find them, we want to actually see if any of them work. We'll go ahead and find all the complex roots. So we have m of x. It's a fourth degree polynomial. Its constant is -6, and its leading coefficient is 2. Now, what I see most students get confused here is they take the ratios in the wrong order. They take ratios of the leading coefficient over the factors of the constant, and you don't want to do that. It's vice versa. It's constant over coefficient. So if you write them down this way, start with your constant, write it up here as a 6 and put a colon. Then you put your leading coefficient 2 and put a colon. Now what we're going to do is we're just going to simply list all the factors of 6, including the negative factors, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So really that's 1, 2, 3, 4 positives and 4 negatives. That's really 8 factors. The factors of 2, plus or minus 1, plus or minus 2. That's 2 positives and 2 negatives for a total of 4. And if we write it as constant over leading coefficient, now we're basically have our numbers stacked like we need to. Now what we need to do is we need to find the possibilities. And to do that, we're just going to have to list all the combinations of the top divided by the bottom. So let's do it. Plus or minus 1 over 1 is plus or minus 1. Plus or minus 1 over 2 is plus or minus 1/2. So I've taken this 1 and I've put it over both of these. Now I'll move to the 2. Same thing. Plus or minus 2 over 1 is plus or minus 2. Plus or minus 2 over 2, well, 2 over 2 is 1. We already have that one listed, so we don't want to write them down again. So now I'll go to 3. Plus or minus 3 over 1 is 3. Plus or minus 3/2. We don't have him yet. That's 1.5. And now we move to the 6. Plus or minus 6 over 1. Well, that's plus or minus 6. And plus or minus 6 divided by 2, that's plus or minus 3. And we already have him. So you want to make sure that if you do write down if you write down all of them, then go through back at the end and make sure that when you simplify them, that there's no repeaters. Because we want to find distinct possible solutions. Well, how many do we have? 1, 2, 3, 4, 5, 6 positives and their negatives. So we have 12 possible rational solutions. Now, what we want to make sure of is that we understand what the theorem says. The theorem doesn't say that one of these has to work or that any of them have to work. The theorem says that if the polynomial that we started with happens to have one, it's got to be one of these. So if we're looking for relatively nice solutions, instead of choosing from the infinite possibilities of x values out there, we've narrowed it down to 12. Okay? None of them are guaranteed to work, but if they're not rational, then we know that they're either going to be irrational or imaginary. And so that kind of gives us some information. Now, back before calculators, this meant that they had to try synthetic division with all 12 of these possible roots. And if they got a remainder, remember, they found one. Okay? Well, we're going to do a little bit better than that. You're going to be able to graph this on your graphing calculator and find some x-intercepts. And your calculator is going to cue you in to which of these possible rational roots work. And in this case, if we graph it, we'll see that two x-intercepts are x equals 1/2 and x equals -2. Okay, so you should be comfortable enough with your calculator to do that. Now that we have two solutions, let's see if they're actually in the category of possibilities. -2, well, that's right there. And positive 1/2, well, there it is. Meaning that I would never dare try a 7. I would never plug a 7 in here to see if I got a 0 because it's not in my list of candidates. Okay? Now I'm going to show you what we can do. We can actually go from here and we can synthetically divide out these two solutions to get what the others are. Okay? So if we start with the degree 4 and I have two real solutions, I can synthetically divide both of them. which will get me down to a quadratic. And once we get to a quadratic, man, we're like round and third coming in home because we can use the quadratic formula or factor or all those other methods. So let's try this. This is a good quick review of synthetic division. We're going to write out our coefficients, 2x to the fourth, 3x cubed, 4x squared, 9x, and negative 6. I'm going to go ahead and do my negative 2 first, just because it's not the fraction, and you want to do the easier numbers first because you're going to make the polynomial smaller. We bring down the 2, and we get negative 4. That gives us negative 1 times negative 2 is 2, 6, that's negative 12, that's negative 3, that's positive 6, and remember the last box is the remainder. We get a remainder of 0, which means negative 2 is a root, or x plus 2 is a factor. Nice. Well, this is our quotient. It's the depressed polynomial. It's 1 degree smaller. If we started with a 4, this is a 3. Well, now I'll do my 1/2 on my result. And so I bring down my 2. That gives me a 1. And I get a 0, 0, 6, 3, 0. So this now is degree 2. 1/2 is a root. X minus 1/2 is a factor. This is 2x squared plus 0x plus 6. And if we're looking for the remaining roots, all we have to do is set it equal to 0. Now notice in this case, since it's a squared term and a constant, we don't have to use the quadratic formula. We don't have to factor. We can solve this one by just separating the variables from the constants and extracting the square roots. So let's do it. We get 2x squared equals negative 6, divide by 2. X squared equals negative 6/2 is negative 3. If I take the square root, I get x equals, and remember, when you take the square root, you take the plus or minus, and this will be the square root of negative 3. Ooh, now the square root of negative 3, is it irrational? Well, it has a negative under the radical. So remember, we can write that as plus or minus the square root of 3 times I outside the radical. So this is precisely where we get our conjugate theorems from. When we have a radical, it could just be plus or minus, or if we have an imaginary, it's plus or minus. But it comes from extracting the square roots. And so these are our other two roots. This is basically the complex conjugate theory. They happen in conjugate pairs. So my 4 roots, are negative 2, 1/2, and the conjugate pair plus or minus square root of 3 times I. Nice. Okay, but we started off by finding the possible rational roots, checking the calculator and verifying. We found 2, synthetically divided, got down to quadratic, and solved our quadratic for the remaining. Okay, now it's time for
Deja Review.
Deja Review. Here we go, a little application today. We've got a grain silo. It's a giant storage bin where grains are stored for future use. And in this case, it's shaped like a cylinder for the base down here with a right circular cone on top. Okay, sheds water very nicely, but I wouldn't want to land on there in a parachute. Kind of pointy. Okay, some of them have kind of like a hemispherical dome to it. But here's what we know about this. We know that it's 30 feet tall, okay, up to the cylinder part, not to the very, very tippy top, the pointy tippy top. And we know that the silo total can hold 1,152 times pi cubic feet of grain at the capacity when it's filled all the way to that pointy tippy top. Here's what we want to know. We want to find the radius x of the silo. Now notice in this diagram, I've defined x to be the radius of the cylinder, which is also the radius of the cone, which in this case will end up being the height of the cone as well. And I want to find what that x is. Okay? So here's what we do. The volume of this thing is composed of the volume of the cylinder plus the volume of the cone. So the volume of a cylinder is equal to pi r squared h. We learned that in geometry. It's the area of the face, the circle, times the height. And the volume of the cone is going to be a third of that. It's pi thirds r squared h. But what I want to do now is, this is a formula off a chart. I want to make it very specific for our diagram. I'm calling the radius x. So here we go. We know the volume of the silo is going to equal pi, the volume of the cylinder, x squared times h. Well, look on the cylinder. This is a constant. It's 30. It doesn't change. So I can actually plug that in. Plus the volume of the cone, which is pi thirds times x squared. What's the height of the cone? Well, it's x. So it's x squared times x. So we get this for the volume of the cylinder, volume of the cone, and we know that that has to equal 1,152 pi units. So now I get this little equation right here. And I want to solve it. So the easiest way, or one of the ways to actually solve an equation on the calculator, is to get everything on one side, set it equal to 0, and then find the roots. Okay? Well, let's go ahead and do that. This is going to be a cubic term, so I'll write it in descending order. I get pi thirds x cubed plus 30 pi x squared. And when I subtract this, I get minus 1,152 pi, and I set it equal to 0. Now, if you were trying to solve this without a calculator, it's not going to be impossible, but I would definitely factor out a pi first. And then you're going to have a coefficient of 1/3 and 1152. So that's going to give you some interesting combinations. This typically for larger numbers is one, once we learn the process, we let our calculator handle the routine calculations. But not until that becomes a routine calculation, which means lots of practice. So if you graph this, we want to think about what a relevant domain is. Because remember, polynomials have domains of all real numbers. So the smallest x can be is my radius is 0. Okay? If I have a 0 radius on the cone, I've basically collapsed my entire cylinder. The largest that x can be is going to be a little bit harder to find. Basically, if you're looking in this formula, if you're letting the height equal 0. I'm going to go ahead and leave this as a question mark because we might not actually need it. But we definitely don't want to have any negative values of x. Okay? So what we do then is we graph this in y1, and we look at a lower bound of 0, and our y value, since we're looking at volume as well, we'll go ahead and look. Well, we're looking for the x-intercept. I'm sorry. I'm getting ahead of myself. When I set it equal to 0, I'm looking for the x-intercept. So if I just graph it in a symmetrical window, like from -10 to 10, that puts the x-axis right in the middle. So you graph that, and you'll find that the x-intercepts are going to be x equals, you get two solutions. You get 6 feet that work. You get one solution that works, that's the only positive one, and then you get two negative solutions, -6.431 and -89.569. Okay? So in this case, since we're talking about a radius and it has to be positive, the two negative solutions, remember it's a cubic, it could have 3, the two negatives don't make sense in the context of this problem. So there you go. The only positive x-intercept is the only positive solution that makes sense. So the radius of this whole thing is 6, or its diameter all the way across is 12. There you go. All right, we're out of time today. As all good things must come to the end, so should today's episode. Polynomials, very important types of functions. There's a lot of things you got to learn to do with polynomials. You're going to get better by practicing. So practice, practice, practice. Starting on the next episode, though, we're going to depart from polynomials. We're going to move on to other types of functions that are very interesting because they have restricted domains, which means there's some taboo values that you cannot plug in to generate a y value. So if that doesn't bring you back to the next episode, I don't know what will. Until then, I'm Kevin Corpy reminding you to do your homework.